Hi everyone, today I'm going to be talking about chapter 9. I'm going to go through circuit symbols and EMF and potential difference. To start with, you'll need to know the circuit symbols for this course and how to draw circuit diagrams using these symbols. We will also talk a little bit about polarity, which is very important in terms of connecting certain components the right way. We'll also look at potential difference, electromotive force, how to distinguish between them, and how to calculate them. And we will also have a look at the electron gun that is linked to this equation. Okay, so the first thing we'll start with is circuit diagrams. Now, every time we draw a component in a circuit or even a circuit, we always need to use the internationally recognized symbols. This is symbols I will show you in a minute. Also, a very important part, when you do draw circuit diagrams, you should not leave any gaps between the lines, and you should usually use a pencil and a ruler. If not, they should be nice and neat. So for example, let's go look at the symbols first and what each one does. So we have the switch. Now the switch is open when you leave the line open, and it's closed when clearly all lines are touching each other. A cell, in real life you usually call a battery. You call it a battery, but we don't call it that in physics. A single cell is a cell. If I connect more than one cell together, we call it a battery. So in other words, if I had this diagram, that means I have connected 1, 2, 3 cells. A very important part is which side is positive and which is negative. The longer one is positive, the shorter one is negative. I usually think of it that if I took the two lines of positive and added them together, they're longer than the negative one. So if you forget that, use that. We have a diode. Now a diode simply allows current to flow in one direction. We will look into more detail into what each component does in the course, but for now, just remember that diodes allows current to flow only in one direction. A very important part of this is that it has to be connected correct due to its polarity. Otherwise it won't work, and I will show you in a second. We have resistor, which is simply a rectangle shape. A variable resistor has a line going through it, so resistor increases the resistance in a circuit and decreases current. A variable resistor, we can fix the resistance and hence decrease or increase the current. A light bulb is simply a lamp, a light bulb, a circle with a cross. You have seen a lot of this in your GCSE, so this shouldn't be that hard. This is a fuse. We draw a rectangle with a line in the middle. You know that the fuse is in the plugs, and if the current going through the fuse is higher than its reading, then it will melt. It's a safety component of plugs at home. A thermistor resistance changes with temperature. So resistance changes, sorry. So if I alter the temperature, the resistance will change, and we'll have a look more into it. An ammeter measures current. A voltmeter measures potential difference, or what you know as voltage, but I don't want to hear the word voltage in A level. LDR, its resistance is a light-dependent resistor. So the word says it all. It means that it depends on light for its resistance to change. An LED is a light-emitting diode. So it only allows current to flow in one direction, and when the current passes a specific limit, it emits light. And a capacitor stores charge. There are a few things that used to help me remember some stuff. So the LDR, the arrows is like a resistor, but with two light arrows going towards it. I used to think of it, since it depends on the light, and the light has to go in. And with the LED, light emitting diode, it gives out light, so the arrows are going outwards away from it. There are a couple more that I wanted to talk about. There's the heater sign. That is a rectangle with two lines in the middle. So this is the heater. You might come across it, it depends. And actually that's just the only one I wanted to see through now. But yeah, these are the symbols that you do need to know for your course. Capacitor we won't come across until the topics of A-level, A2. But please make sure you remember them. Common mistakes are usually done with the thermistor and the variable resistor, so differentiate between the two. So I also mentioned that the diode and the LED have a polarity. Because they let current flow only in one direction, they have to be connected in the correct way. Oh yeah, I also forgot to tell you about the power pack. So a power supply can be drawn as this. Obviously, we're not always going to use batteries, and we always have to write where the positive and negative signs are. So let's say I had, let's go to the polarity now. So this is the positive, this is the negative terminal. If I were to connect my diode, firstly, you need to make sure that there are no gaps in your circuit when you connect the circuit. But if I want to connect a diode, I have to place it in the right direction. Usually we connect it in a way that the conventional current is going through it. So from positive to negative. So the best thing to do is just draw a big arrow like this to show the direction of conventional current, then close it up, and then you have your diode. Or if it was an LED, so a light emitting diode, you just draw two arrows going away from it. So this is a diode or LED connection. It has to be connected from positive to negative, pointing the direction of conventional current. I hope that makes it a bit simpler to remember about how to connect it. So the next bit that we're going to look at now is the potential difference and what it means, the unit volt. So you'll need to be able to define the unit volt as well. Potential difference is defined as the energy transferred per unit charge. I wrote a little bit extra here. So it's the energy transferred per unit charge. I wrote a little bit extra. It's the energy transferred from electrical energy to other forms of energy like heat, light, in a light bulb, for example, per unit charge. The symbol for potential difference is V. And it's always measured in volts. The energy transfer is W. I wanted to mention here, just so that you can remind you quickly, that energy transferred can also be called work done. So it's the same thing as energy transferred. When we say we're doing work, it means we're transferring energy. And then Q is, again, the charge, which is in coulombs. So energy is always in joules as well. So this is the equation. Potential difference is work done per unit charge. And if you look at the definition and the equation, the match, so potential difference is the work done or energy transferred per unit charge. We're going to introduce something new, and I will explain why it matters which way energy is transferred, why we do have different names for certain things. But to do that, I need to go to what electromotive force is, that you see here. Now, electromotive force is simply the energy transferred to the charge carriers, meaning that it comes from a source of energy such as a cell, a battery, or a power supply. And you need to be able to determine what's the difference between EMF and PD in terms of the energy transfers. So it's a very important part of it. So if I draw a circuit, actually, we might make it a bit easier to explain. So in this case, the EMF is what the battery or cell or a power supply will have if there was no current flowing through the supply. Meaning it will be the maximum possible potential difference across the supply. So we call this the energy, the chemical energy stored in a cell, which is transferred to electrical energy carried by the charges in the wires. So for example, if the EMF was 12 volts, that means that 12 joules of energy would be transferred to 1 coulomb of charge. So we have the electrons getting so 1 coulomb worth of electrons getting 12 joules, and they transfer that energy to the light bulb. So we have in the EMF, we have chemical energy being transferred to electrical energy. Then if we look at the potential difference, is the work done by the charge carriers. So is energy transferred by the electrons to components such as light bulb. So it will be electrical energy to other forms such as light, heat, and so on. We also need to define the volt before I continue. So 1 volt across a component is when 1 joule of energy is transferred per 1 coulomb of charge passing through the component. So all we're doing with potential difference in EMF or electromotive force, by the way, this is not a force, even though it transfers energy, it's just simply the potential difference in the battery, but we can't call it that because it has a very specific meaning. So the way to look at it is to think about whether something is losing or the electrons in the wires are losing or gaining energy. So in the case of EMF, the charge carriers are gaining energy, and then they go to a component and they lose it, and this is what we call the potential difference across a component. So to make it a little bit better in terms of definition, EMF is simply the energy transferred from chemical to electrical per unit charge. In terms of the potential difference, is the energy transferred from electrical energy to other forms of energy per unit charge. So this is the difference between EMF and potential difference. If I placed a voltmeter, and this is how we measure voltage, right? We have to place the component parallel to the voltmeter parallel to the component. So if this was a cell that had 6 volts, I will get a reading of 6 volts here. And then if I had two light bulbs, if I didn't have internal resistance in the battery, then they will have values as well, like 3 volts each if there was no internal resistance, but lower if it was. But we'll see that coming on later. This is a very important part of the course. It's a common mistake, a topic that people make common mistakes at, and you'll need to take really good care of what you're doing there. Now, electromotive force is actually given by the symbol epsilon, which is equal to work done per unit charge. It's the same as potential difference, where this symbol stands for EMF, this stands for energy transferred or work done, and this stands for charge. Units are the same, V, volts for potential for EMF, energy is in joules, and charge is in coulombs. So let's do an example together. It says calculate the energy transferred. While we read questions, we underline and label what we need. In 4 hours, by an electrical heater that draws a current and a potential difference across it is 90 volts. So we know that we need to calculate the energy transferred. We know that potential difference is work done per unit charge. That's what we talked about right now. And I know that Q is equal to IT because I'm linking I and T together to get Q. So I can substitute that in there and make one equation. V is equal to work done over current times time. I need to rearrange for energy transferred, so I'll times both sides by IT. T divided by IT is 1. So work done is VIT. And we have 90 times 15 times 4 hours. We need it to be in seconds, remember that. So that's 3,600. We should get 19,000 joules or 19 megajoules. So this is something that you might not get a question about in the exams, but it's very helpful to know. Why do we need to place a voltmeter parallel to a component? Well, the easiest way of thinking about it is that you want to know here how much energy per coulomb, per charge, the electrons had before they passed through the light bulb and transferred that energy, and after you need to know the energy per unit charge that passes through it. That calculates the difference. That's why we call it potential difference. It's a very important part actually, and hopefully that will make a bit more sense. Also, what would be an ideal voltmeter? We know that voltmeters come in a lot of different values and a lot of different shapes and forms, but an ideal voltmeter should in reality have infinite resistance. We saw that an ammeter should have 0 resistance because it has to count the charge per unit time through it. So if it added resistance, then it will take part in the circuit. But the voltmeter needs to have infinite resistance so that it doesn't let any current because if current could go through the voltmeter, then it would mean that the value of the voltmeter itself wouldn't be real because obviously it would have passed some energy to the voltmeter. But even though that's not possible in reality, the voltmeters actually do have a very low high resistance of like millions of ohms. We have one more thing to go through, but before we go through it, I wanted to just do a quick check. We looked at the circuit symbols, circuit diagrams using the symbols. We talked about polarity, which is important. We also talked about the potential difference and its unit volt. EMF, which also has a unit volt. They have the same equation, but it's just different ways of energy being transferred. And we talked about that. And we also looked at the equations in terms of PD and EMF. Remember, EMF is not a force, it's not measured in newtons, its unit is volt. And also, just a quick note here, since potential difference or EMF do have a similar equation, the volt, the unit volt, can be written as joules per coulomb as well. In class, we're going to look at the SI or base units of this as well, so be prepared of that. Just a quick reminder again that epsilon is the symbol used for EMF, so that you don't mix it with E, which is a symbol of energy. The last bit we're going to talk about is the energy transferred for electrons and other charged particles. It is a little bit more heavy in terms of content to understand what this actual equation is, but it's quite nice and easy after. Another thing to quickly mention is that this equation will actually not be given to you. You have to either remember it or figure it out through your own knowledge and work it out. It's quite simple to do after I explain it. So this is not given. These equations are given, and the equation I used in the example here is also given to you in the formula booklet, but this one is not given. Okay, so what we have is an electron gun. An electron gun produces a narrow beam of electrons, okay? There's nothing too special or crazy about it. It's used in a lot of devices. It used to be in TV screens actually before, or computer monitors that are really old. But they're still being used in things like electron microscope or oscilloscopes and so on. They're very useful, and also they teach us a little bit about how electrons interact with matter. But anyway, so electron gun just simply has a hot filament right here, the thing that you see coiled. Now, if you pass current through that hot filament, it will eventually heat up, and the electrons inside the wire here will have enough energy to escape the metal. And that's kind of how they discovered electrons in the first place, when they heated a metal and it emitted electrons, and then there was an electric field and they picked up and it got attracted to the positive terminal. But that's another story for another day. Now, this process of electrons being emitted through the action of heat is called thermionic emission. Thermal, remember, stands for heat. So thermionic emission is the emission of electrons. I always write electrons like this for a shortcut. That means electrons. Through the action of heat. You need to know that word. It's a key term that you do need to know. So this is the cathode. We take the filament, the hot filament, to be the cathode. And this side here is connected to a positive terminal. Now, we know that electrons are attracted to a positive terminal, so there's a potential difference between the cathode and the anode. So this is the anode. So that causes the electrons to accelerate. Now, this whole thing is done in vacuum, so there are no particles in the middle to bump with it. If you remember, we saw the electrons moving in a wire where they were colliding with the positive nuclei of the ions that are fixed there. So we saw that a random movement. That's why we had to calculate mean drift velocity. In this case, nothing is blocking this electron's path. They are just going straight forward. And we can calculate how much energy or work done is done on a single electron using the equations that we just learned. So potential difference is equal to work done per unit charge. Now, in this case, I want to know the energy transferred to each electron. So that's potential difference times charge. And we know that if we are looking at the work done on a single electron between the cathode and anode, then we know that the charge of a single electron here is E, is elementary charge, times the potential difference between the anode and the cathode. Since the electrons are moving now, so they're going from not moving to moving, we know that energy is actually transferred in order to increase its kinetic energy. So half mv squared. So now we come up to the expression that I told you will not be given to you. I'm just equating these two together since they're both equal. So the work done on the electron is used to increase its kinetic energy. Then all that energy goes into the movement of the electron, and hence we come up with this expression. So it's easy to work out due to how you already are aware of this equation and that the kinetic energy is a half mv squared. So here we have the elementary charge, which is 1.6 times 10 to the minus 19. You all remember this now. This is potential difference between the cathode and anode in volts. This is in coulombs. M is for mass, which is in kilograms. And V is the speed or velocity, which is in meters per second. And then since you're squaring it, it's going to be meters squared seconds per second squared. So this expression actually comes from the conservation of energy law. So energy cannot be created or destroyed. It can only be transferred from one form to the other. So if the electrons gain this much amount of energy, it can transfer to the kinetic energy. So it's a good thing to remember that this is an application of the law of conservation of energy. But we are assuming that the electrons had nearly to none energy, kinetic energy, at the cathode to begin with before they escaped the metal. That's a very important assumption here. Now this is an example question. It seems like it only gives you one value, but if you even look at the equation that you do need, it will make sense. These questions usually will only give you one value, but the question itself gives you a little bit more hint. It's telling you to calculate the velocity. So we need to find the velocity of an electron. We know the charge of an electron, and we know the mass of an electron. This is given to you in the formula booklet. From an electron gun with an accelerating potential difference of 4 kilovolts. So voltage is 4,000 volts. Firstly, list the values that you're given and known. Done that. Identify the equation needed. I know that the electron was accelerated from an electron gun, so I know that it gained energy EV, and that energy went into kinetic energy. So I need to rearrange for V. To rearrange for V, I times both sides by 2. So 2 divided by 2 is 1. I divide both sides by M. So I have 2 EV over M is equal to, that cancels with that, sorry, equals to V squared, so the speed, velocity squared, and then we take the square root of both sides. This cancels with this. Remember that square root is the same thing as saying V squared times a half, and when you multiply the two powers, it comes to V to the power of 1, which is V. So then the velocity is square root of 2EV over M. All I have left to do is just simply plug the numbers in. So 2 times 1.6 times 10 to the minus 19 times 4,000 volts divided by the mass of an electron. I think it's 9.11 times 10 to the minus 31. Let me double check. This is at the top of my head. This is given to you in the formula booklet. And I'm correct, yeah. Then when you put the values in the calculator, you will get something of 3.7 times 10 to the 7 meters per second. This is a good point to mention that since the electrons are in a vacuum, they're moving much faster. So it's about 10 times less than the speed of light, which is the fastest speed that you can have. But they're moving much faster than the electrons in a wire, because in the wire they're colliding so many times they don't get to go that far in a specific amount of time. But the electrons in vacuum, they have nothing to collide with. From what we have seen, we have calculated the speed of electrons in a wire to be of the order of 10 to the -4, -5. So you can see how much difference it has for electrons traveling in a vacuum and when they're accelerated, a specific potential difference. If you have any questions about this lesson, please do let me know through Teams or email through RM Unify, whichever way you prefer.